Okay, so let me introduce myself. So, this is Nishchay Shroff, and I am a proud member of Programming Club IIT Indore. So, without a further ado, let's start. Today, we'll be studying number theory part 2 as a part of binary brains course. And the topics which we'll be studying are binary exponentiation, modular exponentiation, inverse of a number with modulo, and GCD LCM and the properties. So, let's start. So binary exponentiation. So suppose I tell you that you need to find a raised to b. How would you do that? We'll do that iteratively, yes. So we'll run a loop from 1 to b and we'll multiply a b times, right? Yes or no? Yeah. Actually, I did not take the last class, so I think you need to ask the concerned tutor. I'm taking this class only, so if you want to say, if you have any doubts, you can tell me right now also. Even if if you don't get anything, then you can tell me whenever you want to during the class, even after the class as well. That is what I'm telling right now, right? Binary exponentiation, the basic motto is to find a raised to b with smaller time complexity. So you tell me one thing, if you want to find a raised to b, how would you do that? I tell you, I give you a, I give you b, and I ask you to find a raised to b. How would you do that? Hello. Yeah, you tell me the logic only, no need to write the code. What would you do exactly? Yeah, so you'll take one. Okay, I'll write the code for you. So, see, you'll take a variable answer equal to 1. Okay, and then you'll run a for loop for I. I'm just writing a pseudo code. Okay, you write in whatever language you want to. I from 1 to b. Okay, and we'll do answer is equal to answer multiplied with a. So this process would happen b times. So in the variable answer, you will get an a raised to b, right or wrong? So what is the time complexity of this program? You know time complexity, right? What's the time complexity here? O of b, right? Right, because this loop will run b times, so the complexity would be O of b. Now, the basic motto of binary exponentiation is to reduce this time complexity from O of b to O of log b. Okay, so that is what we'll be doing in binary exponentiation. Now, is it clear what we're going to do? Fair enough. Okay, let's start. So, this, as I said, what we'll be doing is basically we'll be reducing the time complexity from O of b to O of log b. And this is something to really note. The power function that we use in C++, you know that, right? Maths, it is in the maths header, like in hash include math.h. This power function is present. So its complexity is O of n. Like it will be iteratively finding the power, right? So this you must remember. When you use the inbuilt function, the time complexity is not O of or not O of log n, it's O of n. Okay, so let's move ahead. Okay, so the binary exponential revolves around this funda. If b is even, you can write a raised to be equal to a raised to b by 2 into a raised to b by 2. So somehow if you can compute a raised to b by 2 and a raised to b by 2, you can easily multiply it 2 times to find a raised to b. Suppose if b is odd, then a raised to b by 2 into a raised to b by 2 into a raised to a would give you a raised to b. So if somehow you can find a raised to b, a raised to b by 2 and a raised to b by 2, here b by 2 means seal of b by 2, right? Since b is odd, b won't be divisible by 2. So b by 2 itself means seal of b by 2. So a raised to c of b by 2 into a raised to c of b by 2, and then if you multiply it with a, you'll get a of b. So what we'll be doing is we'll build a recursive function for that, and that recursive function will help us to calculate a raised to b by 2 for us, and then we'll multiply with it two times and then multiply it with a to find a raised to b if b is odd, and we'll just multiply it twice if it is even. So I'll show you the code how we write it. Is this funda clear? What we are going to do? We'll recursively calculate a raised to b by 2. So the function is like this. So I have a function. It will take a and b as variables. Sorry, as arguments, and then I'll recursively call. I'll take a value and I'll call a comma b by 2. B by 2 itself means seal of b by 2, right? And then if b is odd, then what will we return? Return x into a, right? A of b by 2 into a of b by 2 into a, right? So it would give us a raised to b, and else you simply multiply it twice, return x into x. Okay, so what we did, we divided the search space into two halves and we separately calculated each of them. So the time complexity would be reduced to from O of n to O of log n, right? Because we are every time dividing b by 2. Getting the point or not? Hello? You know it is similar to binary search, right? In binary search also we divide the search space into half. First we search from 1 to n, we find the mid, and then we search only for half the part. We leave the other part. So something similar is happening over here. You see, we are finding for b by 2, we are again going dividing by 2, we keep on dividing by 2 until, and one more thing I forgot to add, the base case. If b is 0, then we simply return 1, right? Because a raised to 0 is 1. Is this clear to everybody? Hello? Okay. So, are you guys able to know that the complexity of this is O of log n, right? Because we are dividing by 2. Or anybody having any questions? Hello? Okay. So, in this way, we calculate a raised to b in time complexity O of log n. So, this is a recursive way. Now, we also have an iterative way. So, in iterative way, what we do is, we write b in its binary form. Let's say b is 10111, something like this. And so, when you write it in binary form and we iterate it, okay, so I'll tell you in some simpler way. So, what basically we do it is, we keep on dividing b by 2, right? And whenever we get a remainder 1, we multiply it with a. So I'll show the code only, it would be much more clearer. So you see this code, this c is our answer which we'll be storing, and then we'll move inside the loop, and if we find the remainder of b to be equal to 1, we multiply it to our answer. So what basically we do is we break it down into powers of 2. So let's say I need to find a raised to power 13. So I can write it as a raised to power 8 multiply with a raised to power 4 multiply with a, right? 8 plus 4 plus 1. So I broke it down into powers of 2. Now what I'll do is, in each iteration I'll keep on multiplying a. So first I'll say I have 13. 13 divided by 2, the remainder is 1. So we'll multiply our answer with a. So answer now becomes a. Okay. Now we divide 30. See, what basically the funda which we are applying is, we keep on dividing the number by 2, right? And in the same process, we keep on multiplying a with itself. So a in one iteration is a, then it becomes a square, then it becomes a to the power 4, then it becomes a to the power 8, and so on, right? So why are we doing that? Because we only want to compute a in powers of 2. We only want a raised to 8, a raised to 4. There is no need for a raised to 3, 5 or anything like that. We only want the powers of 2, right? And then what we'll be doing is we'll be decomposing the power b into powers of 2. We can write 13 to be equal to 8 plus 4 plus 1, right? Yeah, so how would we do that? You know how to convert a number into its binary form, right? We keep on dividing by 2. If the remainder turns out to be 1, then we add that remainder and reverse it, right? This is what we do. So that is what we'll be doing. We'll keep on dividing b, that power. So b is initially 13. First we'll divide by 2. We find the remainder is equal to 1, right? So we'll multiply our answer with a. So now the answer will become 1. Initially it was equal to 1. Now our answer will equal to a, right? Now we'll divide a by 2. So now a becomes 6, right? Now we check 6 divided by 2. So the remainder is 0. So we won't do anything else. But at the same time, we would make a to be equal to a square. You see over here. See, if b is divisible by, if b mod 2 is equal to 1, we multiply c with a. But in every iteration, we are multiplying a with itself, right? So in each iteration, we will be having the power of 2. So first it would be a, then it would become a square, then it would become a to the power 4, then it would become 8 to the power 8, and so on. Is this clear to all? Hello? C is the answer which we want. See, first, let's say you want to find a raised to power 13. First, b was 13, right? C was 1. So 13 divided by 2 is equal to 1. So now C will become a. Okay. Now we'll make a to be equal to a square because we are multiplying it with itself, right? And we make b to be equal to half of it. So it will become 6. Now you see 6 is divisible by 2. No, alright. 6 divided by 2 is 0. So we won't do anything. Now we want the first power where the remainder is equal to 1. Because when the remainder is equal to 1, that would be a 1 in the binary form. Right? When you write when you write that when the remainder is 1, that would be a 1 in the binary form. So we are only multiplying with those powers which are actually 1 in the binary form, right? Yeah, exactly. Because binary, when you convert to binary, if a number is x, then in binary form it would have log x numbers, right? So if the number is, let's say, 16, so it would have 5 bits. So we only need to perform 5 iterations maximum. Getting the point or not? So the time complexity is reduced from n to log n. Getting the point or not? So this is, yeah, good. Yeah, exactly. In iterative way, we would be multiplying every time with a only. Here, what we are doing, we are only computing the powers of 2, and then we are expressing the number, the power, the value b as the sum of powers of 2, right? And we are simply multiplying them. So the complexity is reduced, right? So is this process clear to everybody or not? Hello? Anybody having any questions? Okay. So let's move to the next slide. Okay. Modular exponentiation. So this is exactly the same as exponentiation, except for the fact that here we need to compute a to the power p and we need to compute its remainder on dividing by m, where m would be any kind of number. Generally, it's a prime number in competitive programming, right? Now, are you aware of this thing that when we multiply, the remainders also get multiplied? If we multiply two numbers, then the remainders with a fixed number also get multiplied. So a into b mod m is equal to a mod m into b mod m and whole mod m. You know this or not? Hello? Exactly. So it's not a big deal. So what we'll be doing is we'll run the same code which we did here, and instead of just writing C into C, we would write C mod m into C mod m, and here we would write C mod m into C mod m into A mod m whole mod m. So we'll just add remainders to it. modulo m to it. The rest of the code will still be the same. Getting the point? Hello? Okay, so I'll show you the code. See, the same code is written over here, C into C mod m, and here you see C into C mod m whole mod m. Okay, now here you don't write C into C mod m, because when you write C into C mod m and then you multiply with A, then there might be a possibility that it may lead to overflow. So you write it systematically. So okay, I'll tell you how. Suppose you want to write A into B into C. Okay, let's say you are given something like this, and you want to write it mod m. So what you will do is you write A mod m, okay, into B, then you divide again by mod m, okay, then you multiply with C, and you again mod m, okay. So there is a lesser chance of getting overflowed. Suppose you simply do like this: you multiply A into B into C, and if the numbers are very large, then it suppose A, B, and C are all less than 10 to the power 9, let's say. So A into B into C might exceed 10 to the power 18. So it might exceed long only. So you won't be able to store this in a variable, right? So to avoid such kind of errors, first you do is you keep on finding remainder at every step, which I did over here. Getting the point or not? Hello? Yeah, yeah, yeah. So in many competitive programming questions, you would be asked to find something modulo 10 to the power 9, so that you can, because you will be asked to find something modulo 10 to the power 9 plus 7. So why are we asked to do that? Because we want to store the answer in an int variable. So when you find remainder with 10 to the power 9 plus 7, you can store it in an int variable, right? Okay. Yeah, the question itself will ask you exactly. Or sometimes you might also have to find something like this. So you might also be asked to find something like 100 or 102 to the power 10 raised to 5. Like you are given an array and you need to you need to find something like this. Now you can't store in any variable, right? Even in long whatever you want to do, you can't store this value, right? So the finding remainder becomes mandatory in this case. There might be questions like this also, where you need to find a very large power which can't be stored in any variable. So for that purposes, it is mandatory to find it modulo something, right? So that's why modular exponentiation is being taught, right? It will be used in competitive programming to store large numbers in a smaller form, basically. The code is still the same, but you just need to make sure that the you just need to minimize the chances of overflow by doing something like this. You keep on finding modulo at every step. First you find A mod m, then you multiply with B. You can also write B mod m here also, because there might be a possibility that B is also greater, right? So A mod m, you multiply with B mod m, you again take a remainder, then you multiply with C mod m, and you again do mod m. Is this clear to everybody? Hello? Okay, so it's very trivial. You take A into B to be equal to X. See, then you again apply the formula. You can generalize for any number of variables, A into B into C into D, or any number of variables. It would still be the same, right? Okay, so is this concept clear to everybody? The modular exponentiation is exactly the same as binary one, except we are finding the remainder. That's all. Okay, so let's move ahead. Modular inverse. So, modular inverse of a number is, let's say you. Okay, I'll tell you the exact definition of that by writing. So, yeah, example. So let's say you need to find 2 to the power 7, let's say, right? So in what method do you want? Recursive or okay, I'll tell you in recursive method only. Yeah, there are two parts for that, no? See, you understood binary exponentiation or not? You tell me first. So modular exponentiation is exactly the same. The only thing you need to do is you need to just take a remainder of it. Nothing else. You see the code over here. See this. You see this code, the modular exponentiation code and the binary exponentiation code. It is exactly the same. Only here they have taken remainder modulo m. So basically you need to find something modulo m. That's all. Rest everything is the same. So if you have understood binary exponentiation, sorry, if you have understood binary exponentiation, everything is same only. See this. You compare the code. The exact same code is there. No, we don't need to get that. That's why we are taking remainder. The purpose of deliberately introducing a modulus is to store a large value in a smaller format. There, in competitive programming, there are cases where you need to find powers as large as something like 10 to the power 5. You need to find something like 1200 raised to power 10 to the power 5 or something like that. Now you don't have any variable where you can store such kind of big values. Getting the point? Okay. In permutation combination questions, such kind of big values may be generated. So to store them into a smaller format, we use this modular exponentiation. This is an exponent, right? This might be an answer to some problem, right? Some PNC problem or anything like that. So to store it into a smaller format, we introduce this funda of taking the remainder. So we don't need to actually get back to the original answer. We just need to store the remainder. Getting the point? Rest everything is the same. Yeah, yeah. They ask in remainder form only. Generally, remainder modulo some large number closer to 10 to the power 9 because the range of integer is near to 10 to the power 9, no? So basically, you can store it in an int variable. No, you don't need to choose. In most of the questions, you will be given that. Okay. So shall we move ahead? So I was talking about modulo inverse. So I'll tell you what exactly is a modulo inverse. Let's say if x is a modulo inverse of a, then a into x modulo some number should be equal to 1. Getting the point? If x is a modulo inverse of a, right, with respect to m, okay, then a into x mod m should be equal to 1. That is what it means. Okay, when you multiply a into x and you take the remainder mod m, you will get 1. That is the definition. Okay, so the if m is not a prime number, then there can be more than one value of x for a given value of a. Right? I don't. The proof is beyond the scope of this discussion, but you must remember that if m is prime, then the result will not be unique. There will be more than one modulo inverse which you can get. However, if m is a prime number, then there would be exactly one number which would be a modulo inverse of that. Okay. So in some cases in competitive programming, you might be you let's say you want to find something like this: a by b modulo m, right? So this you can write as a modulo m times mod inverse b modulo m and whole modulo m only when mod inverse is unique. Getting the point or not? Hello, right? So you can only do this when mod inverse is unique. If you are getting more than one mod inverse, this makes no sense, right? And the mod inverse is unique only when the number m is a prime number. Is this clear to everybody? Hello? Yes. Okay, so let's move ahead. Okay, so let's move ahead. So if you want to complete modular inverse, this is a naive method. So naive method basically means you iterate over all the possible values and try to satisfy this criteria. Extended Euclidean theorem is beyond the scope of this discussion, but it will also find all the possibilities. What we'll be studying right now would be Fermat's little theorem, and this is because it works only for prime numbers and it will exactly give you the unique modular inverse which we want to find, right? We only the modular inverse is only worth when we have when the number is prime, because then it would be a unique number. If the m is not prime, then we would get more than one answer, so that doesn't satisfy our purpose. Okay, so we'll move on to Fermat's little theorem. Okay, so this is the Fermat's little theorem. According to Fermat's little theorem, A inverse, that the modulo inverse, is equal to A to the power m minus 2 mod m. So if you can compute A to the power m minus 2 mod m, then that is exactly equal to the mod inverse. Is this clear to everybody? Right? So if you want to find inverse, and this is only valid when the number m is prime. Please make it a point. When m is prime, only then you can do this. Okay, and in most of the questions in competitive programming, m would be something like 10 to the power 9 plus 7 or 10 to the power 9 minus 7 or something like that. So that basically itself is a prime number, right? If you verify it, 10 to the power 9 plus 7 is a prime number, and then you might be asked to find an inverse, so you can easily do this, a to the power m minus 2 mod m, and you can do this using binary exponentiation, which we studied just now. Using this thing, you put b to be equal to m minus 2, and whatever you get would be the modular inverse. Getting the point or not? Okay, so this is what modular inverse is, and why I showed the purpose why we find it. If you want to find something like this, a divided by b mod m, then you can do something like this: a mod m times mod inverse b mod m and whole mod m. Getting the point or not? Right? So here we use mod inverse. You can do something like this. This thing is not equal to, a mod m divided by b mod m whole mod m. You can't write something like this. Okay, this is incorrect. So you need to find the mod inverse for that. Is this clear to everybody or not? Okay, so let's move ahead. Now we'll be studying greatest common divisor. So, and least common multiple. So GCD, or greatest common divisor, is the largest number that is a divisor of both A and B. So if GCD of AB is X, then both A and B are divisible by X, and no other element greater than X are divisible by A and B. Okay. GCD is the largest number that can divide both X, A and B. And same is the case with LCM. LCM is lowest common multiple, as the name suggests. So it is the smallest multiple of both A and B. So LCM is divisible by LCM divides A, LCM divides B, and it is the smallest number that does it. Is this clear to everybody? So I'll give you a few examples for that. If I ask you, what is the GCD of 8, 6? What will be the answer? Hello? Okay. And if I ask you, what is the LCM of 4, let's say 15? What would be the answer? Okay, so everybody is clear with what is GCD and LCM. So now we'll be studying few properties of GCD and LCM. And one more thing which I want to tell you, that GCD of, when any number is 0, GCD of A and 0 is always the number itself. GCD of A, 0, anything 0 is the number itself. Okay. because anything 0 is divisible by everything, right? 0 mod 1 is 0, 0 is divisible by 2, 0 is divisible by 3. So the largest number that is divisible, that is a factor of both a and 0 is a itself, right? Because 0 is factor of everything. Okay, so this is clear to everybody. Okay, so let's move ahead. Okay, so now we want to compute GCD. Okay, so for that purpose we have Euclidean's algorithm. So Euclidean's algorithm says that GCD of a comma b is same as GCD of a mod b and b. Okay, this is what the Euclidean's theorem says. So what we do is we replace a with a comma b and recursively try to find GCD until we get the remainder to be equal to 0. So I'll show you the code. See, if a turns out to be equal to 0, then we'll return b. Okay, so I replace. So it should be b mod a and a mod b. Here it should be b mod a and a. Okay, so b mod a and a. Okay, so this is the Euclidean's theorem. I won't be proving it right now. It basically says, this is what it says. GCD of A and B is equal to GCD of B mod A and A. These two are exactly identical. So we exploit that property. We keep on recursively finding GCD of B, A and A until we get A to be equal to 0. The moment we get A to be equal to 0, that GCD would be B, and that is our answer. Right or wrong? We already showed that, like GCD of anything with 0 is a number itself. So when we get A to be equal to 0, the answer would be B. So is this code clear to everybody? Okay, and I think in the iterative we are also doing the exact same process. We are iterating till A is greater than 0. We are replacing A with B mod A and B with this A only. See, this is what we are doing exactly over here. You see this? Till A is greater than 0, we replace A with B mod A and B with A. And the moment we get A to be equal to 0, that is our GCD. Okay, is this clear? Okay, okay. So LCM we already studied what is LCM. Now I'll show you one interesting property. It is a proven fact that LCM of two numbers into the GCD of two numbers, that is always equal to the product of two numbers. Always true. Right? So you remember this. Okay, and how does this come? So I'll tell you intuitively. So suppose you prime factorize A. You know what is prime factorization, right? Hello? Yes. So we write A to be equal to P to the power P1 into Q to the power Q1 and so on. Similarly, we write B to be equal to P to the power P1 dash and Q to be equal to and Q to the power Q1 dash and so on. Okay, then GCD would be equal to P to the power minimum of P1 comma P1 dash times Q to the power minimum of Q1 comma Q1 dash. Okay, okay, so can everybody get why is this happening? Hello? Are you guys able to understand why is this true? Right? The largest divisor would be the smaller power of both of them, right? Then only exactly, then only it will divide. Similarly, if I want to write LCM, so LCM would be equal to P to the power the maximum of both of them, right? P1 comma P1 dash times Q raised to max Q1 comma Q1 Q1 dash. Okay, and so on. Right or wrong? So these two things you should also remember, right? GCD is when you take the minimum powers, and LCM is when you take the maximum powers. Right? Now you see, if you multiply GCD and LCM, one of them would be minimum, one of them would be maximum. Right? So GCD and LCM would be equal to P1 P to the power P1 dash plus P1 plus P1 dash, right or wrong? See, when you multiply, so okay, so if P1 is equal to minimum, then P1 dash will be equal to maximum, right or wrong? So when you multiply both of them, you will be ultimately getting P raised to power P1 plus P1 dash, which is exactly equal to A into B. Okay, so that is why LCM into GCD is also equal to the product of two numbers. That you can prove it using this thing intuitively. Okay, hello, is this clear to you or not? Okay, so we said that A into B is equal to GCD into LCM. So LCM is basically A into B by GCD, right? You can compute GCD using the Euclidean algorithm, and then from that you can compute the LCM also. Okay, and if you guys are using C++ language, then there is an inbuilt function to calculate GCD. Something like this: underscore underscore GCD, two times underscore and then GCD, and then you write the two numbers A and B. So when you write something like this, it will give you the GCD. It will return the GCD directly. No need to write the Euclidean score, but only for C++. I don't know about other languages. For C++, there is an inbuilt function like this. And if you don't want this inbuilt function, then you can go with the Euclidean algorithm also. That is also fine. Okay? It is same as that of Euclidean algorithm. Exact same. Okay, so let's move ahead. But yeah, make sure that these arguments are of the same data type. Like if A is in long long, then B should also be in long long. And if A is in int, then B should also be in int. The data type of both the variables should be same. That is all you need to ensure. Okay, in inbuilt function. Otherwise, it will give you an error. Hello. Yeah. So let's move ahead. Okay. So these are some properties of GCD and LCM. We'll be studying them one on one. The first two properties I already explained, right? For each prime factor, we'll just take the minimum of both of them. Here we'll take the maximum of both of them. Okay. Now, if you want to find GCD of a series of numbers, so what you do is, suppose you want to find GCD of A, comma B, comma C, comma D. So that is exactly equal to of A, comma B, GCD of A, comma B, comma C, and then you again take GCD. Something like this. First you take the GCD of A, comma B. Whatever answer you get, you take its GCD with C. Whatever answer you get, you again take GCD with D. So if you keep on repeating that process, the final answer that you would get would be the GCD of all the four numbers. Is this point clear to everybody? So I'll give you. Okay, so yeah. Now the question comes that why is it true? Right. So in order to prove it, let's say we'll prove it for three numbers A, B, C. Okay, and we can generalize. So if you write A and B in this form, prime numbers form, right? And we again have C something to be P to the power P1 double dash times Q to the power Q1 double dash and so on. Right. Then if I ask you what is the GCD of A comma B comma C, right? You would simply say that would be exactly equal to when you take P to the power minimum of all of them P1 P1 dash P1 double dash, right? And same way Q to the power minimum of Q1 Q1 dash Q1 double dash, right or wrong? Okay. So okay, so this is GCD and we keep on repeating the process. Now what is GCD of? Now what you do, now you first take GCD of A comma B. Okay, that is equal to P raised to minimum of P1. Okay, so I'll write directly the point. Okay, now we want to find the other thing, the GCD of A comma B Okay. Now we need to find something like this. GCD of A and B and then with C. What would be that equal to? P to the power minimum of minimum of P1 comma P1 dash comma P1 double dash. Right or wrong? So minimum of P1 comma P1 dash is what we get from GCD of A comma B, and then we again take its minimum with P1 double dash. Right or wrong? Yes or no? Okay. Yes. And we do the same process with Q also. Okay. So isn't this thing equal to the minimum of all of them? Minimum of P1 comma P1 dash comma P1 double dash is equal to minimum of all three of them. Right? So that shows that this thing is equal to this thing. Right or wrong? So you can take any combination of that. You can also say that is equal to GCD of B comma C and then with A. That is equal to GCD of A comma C and then with B. Whatever order you wish to do, you can do it. But finally, the answer that you get would be equal to GCD of all three of them. Okay. And same is the case with LCM also, because in case of LCM, instead of minimum, we would be taking maximum. That's all. No difference. Rest everything is the same. Okay. So I think these two properties are pretty clear. The third and the fourth properties, right? I proved it just now. Okay, and this one is pretty obvious, which we studied just now. That also I proved it to you using this funda, product of minimum and maximum. Okay, so the only property left is GCD of A comma A plus 1 is equal to 1. Or in other words, two consecutive numbers are always co-prime. You know what is co-prime number, right? Co-prime number is the one. If two numbers are co-prime, then the GCD is 1. Yes? So two consecutive numbers are always co-prime. That is you need to remember. Now how I'll show you. So let's say for time being you assume that GCD of A comma A plus 1 is equal to something K, and you assume K to be greater than 1. Okay. So since GCD is equal to K, you can write A to be equal to K into A1, and you can write A plus 1 to be equal to K into A2, right? Because GCD is a factor of A and A plus 1, right? So A and A plus 1 both will be divisible by K. Okay. So now we simply subtract these equations. Let's see what we get. So we'll get 1 to be equal to K into A2 minus A1, right? And we know that both A1 and A2 are integers. Okay. And K is also integer. Okay. So what we are getting is the product of two integers is equal to 1, right? And both are positive. No, none of the integers is negative, right? We are talking about positive numbers. Okay, by default they are positive. So both should be equal to 1, but that contradicts our assumption that K is greater than 1, right? Hence K has to be equal to 1. Okay, is this clear to everybody? Proof by contradiction. Okay. So I think the properties are pretty clear. If anybody has any question, please share, or we'll move ahead with the next topic. Anybody, any questions? Or shall we move ahead? Okay, fine then. So, okay, the last topic. Okay. So now we'll be studying Euler's totient function. So, Euler's totient function is basically a function that is used to calculate all the values of all the number of values that are less than n and they are co-prime to n. Or in other words, Euler's function will give you the count of all the numbers which are less than n and the GCD of those numbers with n is equal to 1. Right? Uh, okay, so the formula for that is, okay, so if you want to find the Euler's totient function, one very brute force method would be you iterate for all numbers from 1 to n and you find GCD of each number with n. So for I from 1 to n, okay, you find GCD of I, find GCD I comma n. Okay, if GCD is equal to 1, then you increment the count, and this count is equal to the torsion function, right? You initialize the count to be equal to 0. This is a very brute force approach, right? Now, mathematically, this function came out to be something like this. So let's say the torsion function is phi of n, that is equal to n into 1 minus 1 by p1 into 1 minus 1 by p2, so on. Where what are p1, p2? p1 comma p2 are all prime factors of n. Okay. So if you want to count all the numbers that are less than n and the GCD of those numbers with n is equal to 1, you simply apply this formula. You take n, do its prime factorization, and put all the prime factors over here and find answer. That's all. Right? This would always give you a count of all the numbers less than n and co-prime to n. Fine. One way of doing it is using brute force. You iterate for all the numbers. The second way is simply using this formula. So the time complexity of finding the Euler's function would simply be the time complexity of prime factorization, which is less than O of n, if you want to, right? If you know the prime factorization, it becomes very easy. Is this clear to everybody? Okay, so I think we are done with what we wanted to. So these are the problems, guys. Please practice these problems, and if you have any questions, do let me know in the Discord channel. People will help you out. And okay, so we are done with our class. If you guys have any doubts, please ask me. Otherwise, we'll wrap up. Hello. This torsion function. Torsion function. See, torsion function. What is torsion function? So basically, torsion function. This is, we call it phi. Phi of n is equal to torsion function. Okay. So what it gives is, it gives you the count of all the numbers less than n and co-prime to n, right? So let's say your n is equal to, let's say, 12. So you count all the numbers that are co-prime to. 2 is co-prime? No. 3 is co-prime? No. 4 is, you know what is co-prime number, right? Do you know what is a co-prime number? Right. So if I give you n to be equal to 12, how many numbers would be there which are less than 12 and they are co-prime to 12? That count of numbers would be given by this torsion function. Is this clear? What is torsion function? Right? Now, if you want to find the count, there is one brute force approach. What you do is you initialize count to be equal to 0. You iterate for all numbers from 1 to n, and you find GCD. Co-prime numbers by default mean the GCD of both of them is equal to 1. Right? 1 by 1. Yeah, that itself is brute force method. That is brute force method, right? This is one method. Now, mathematically, it has been proven that that function comes out to be something like this, which I have written just now. Right? N times 1 minus 1 by p1 times 1 minus 1 by p2 and so on. What are p1, p2? P1, p2 are all prime factors. Prime factors, not factors, they are prime factors. Okay, now how would you find prime factors? Complexity of finding prime factor O of root n. You can do it in O of root n or not. Right? So the time complexity is reduced basically from O of n. Here the complexity was O of n. Here the complexity is O of root n. Something like that if you want to, right? So that function turns out to be something like this. When you put values, you will get the count of those numbers which are less than n and they are co-prime to it. Okay, so that is what torsion function is about. It is not mentioned over here, but if you Google it, I think in GFG or something like that, you will get the exact formula also, which I'm telling you this formula. It is not mentioned in the slides, but this is the exact formula for finding the torsion function. Now is it clear? Okay, fair enough. So anybody having any questions, any further doubts? Okay, so we'll wrap up the class. So thank you guys for attending. See you later. Bye.